Hello again. This is Dr. Tom with a lesson on heat exchangers for Thermal Fluid and Systems Week 18, specifically on the LMTD correction and the Epsilon-NTU method. So let's get started. When a heat exchanger is not a parallel or counterflow configuration, meaning it is either a cross-flow or multiple pass type design, a correction factor, F sub C, must be applied to the LMT value from the standard LMTD calculation. The notation will be a delta T sub Ln for log mean. And recall that this log mean temperature difference, delta TLM for short, is a delta TA minus a delta TB divided by the Ln of delta TA over delta TB. And those two terms, delta TA, are the difference in the temperature hot and cold for one end of the exchanger and the other is for the other end, and it really doesn't make any difference how you set it up. It will remarkably come out to be the same value. So this is what we did in the last lesson, and we got down really to this particular point and talked about there needed to be a correction. Well, now we're going to actually calculate one. Be careful now that you've got to apply this to whatever design you have that's not parallel or counterflow, is that you need to calculate the LMTD for counterflow arrangement. Okay, that's what you're going to multiply the F sub C by, so be careful about that. The MERM, there's lots of charts out there. MERM has an appendix that has actually four common configurations to find F sub C. One of them is the one shell pass, an even number of tube passes back and forth, so you get an even number of parallel and cross-flow, counterflow configurations. And then they've got a two shell passes, four tube passes, one shell pass with three passes that are two counterflow and one parallel, kind of unusual. That's out there. And then a cross flow shell, one tube pass, but one fluid is mixed. So I recommend finding either in your heat transfer text, if you have that, or just acquire a chart off the internet. I kind of Googled this kind of thing, and of course under images you have more than you can possibly deal with, but I'd find that one and maybe a couple of others that you might want to have, and put it in your PRN here that you have those. Okay, just a recommendation. Now, once a correction factor F sub C has been determined, then it can be used in the equation for the total heat load Q. Q is UA delta T corrected, where the Q is the heating load, the U is the overall heat transfer coefficient, which we saw how we actually calculated, but in these problems you're going to be given it. It's too much to have you do that as well as the other part. A is the heat transfer area. Sometimes that's actually asked for. And then, of course, the delta TLM is the abbreviation for LMTD for a counterflow design here. So really the second term up there is what we're going to use, UA F sub C that we find times the delta T that we're going to calculate. Okay, well let's do an example here. Let's read through this together here. We want to determine the heat transfer area, okay, required for a two shell pass, four tube pass heat exchanger design. Okay, so it's not parallel or counterflow, so we got to have a correction. Water on the shell side is cooled from 20 degrees C to 5 degrees C by a brine mixture, salt mixture on the tube side that enters at minus 2 degrees C and gets warmed up to 3 degrees C. The overall heat transfer coefficient is given to you as 500 watts per meter squared degree C. Again, these are just numbers people just use. And the heat load is given in this particular case as 25,000 watts, or it could have been given to you as 25 kilowatts. So either way, you may see that. Okay. Okay, well, the first thing to do is to find that LMTD for counterflow design, even though this is not that design, but do it. And I can't strongly recommend to draw a little diagram like this. We did this in the last week's lessons, drawing both the parallel and counterflow. It helps you with all kinds of things that you would have to do here. Okay, so on the top you've got the water is at 20 and it's going to drop. It's not really the hotter. Going to drop to 5, and then the brine -2 is going to be the cold side going up to 3 here. So that's the actual design here. So the delta TA, A is usually on the left, so we've got 20 -3 or 17 degrees C for its delta T. On the right is 5, and watch the double negative. 5 minus a -2 gives you 7. If you don't catch that, I'm sure that's answer A. Well, maybe not on my ABC, but certainly the NCS would do that. Okay, so you've got those two. So now you can use the LMTD standard equation that we did in the last lesson to come up with the LMTD for counterflow of 11.3 degrees C. 11 might have been okay, but one decimal point is probably plenty. Okay, so we've got that. So now we got to find F sub C. Okay, well, to use the charts, you're going to have to come up with some terms here. One is this term referred to as a P in some references. It's the and you got to watch, and that's why that picture on the previous slide is so important, is to find the temperatures, tube out minus tube in. That's the brine, and then the shell, which is the water in minus the tube in. And so if you lose your mind trying to figure out which one's going on here, you've got the numerator is 3 minus a -2 again, which is 5, and then the denominator is 20 minus a -2, so you got 22. 5 over 22 gives you 0.23. So that's one of the variables in the chart. The other one is referred to as R. Again, T shell in minus T shell out over T tube out minus T tube in. So you've got 20 minus 5. That's the water. So that's 15. And you got the tube out minus tube in, 3 minus a -2, which is 5. 15 over 5 is 3. Okay, so that's the other quantity that you need. Okay. Now, going to the chart that is in the MERM, using those particular two values, I kind of read it at about 0.97, okay, somewhere along in there. You might read 9.6, maybe 9.8, but I don't think the answers will be close enough to where that would have been an issue, okay? They just can't do that. You can't read that chart any more accurate than that, okay? So, we can now find the area. We take our equation Q equal U AFC delta M, solve for A. We got the Q, we already have the load. We have the U, we now have the F sub C and the delta LM. We could got all those. So substituting and watching units, we've got, remember, if the units don't work out, you can't, it doesn't matter what the number is. And in heat transfer, for sure, if you can make the units come out, you probably got the right answer. You've accounted for everything. Okay, even in my textbook, I was a very astute author and whatever, have highest respect for and everything, and darned if he didn't get some of the units wrong. It's just typos, but I guess, well, what happened to the degree C? Well, it's because I had the wrong units. Okay, so you got to watch that. So we have watts in the numerator, we've got the U's got watts in the denominator, so that goes away. In the denominator, you got per degree C times degree C, that goes away. So the 1 over meter squared in the denominator ends up in the numerator. So yeah, we do have meters squared. So now get your calculator out and do that. And again, watch your calculator as well. Okay, and I get 4.56 square meters. Okay. Okay. This is again two-parter. One is about the LMT correction. The other is referred to as, that's an E. It looks like an E, but it's really in the Greek letter epsilon, Epsilon-NTU method. This method is when all the temperatures are not known. The LMT method works great. You got to have all those temperatures though, the inlet, both inlets and both outlets. But for problems in which you have the only the entering temperatures, then you got to have a different approach. Okay, so you could try to use it as textbooks say. You could try to use the LMT method, but it would be a iterative process and might not converge very rapidly. So this is definitely a considerably more straightforward approach here. Okay, so this ultimate approach is the Epsilon-NTU method. Epsilon is called is the effectiveness percent. It's a ratio of two heat transfers. We'll get to here in a minute. Heat transfer rates, and the NTU stands for the number of heat transfer units. They used an NTU. They didn't want to do an NHTU. I guess they already had enough four-letter acronyms in LMTD. Somehow I think you're supposed to leave it to 3, kind of thing. So, but that's what that stands for. We'll talk more about what it is. First, the effectiveness percent, because it's going to really be a decimal. It's percent, but you'll be using, say, a decimal, is the actual heat transfer rate divided by the maximum possible heat transfer rate. Okay, so what's going to happen is we're going to actually come up with an expression for Q max. We'll find epsilon, and then we'll be able to calculate Q. Okay, now the effectiveness varies with the design of the heat exchanger. These can be obtained from formulas or charts. The MERM has 7 such charts, nice charts. Use them in the examples here, the challenge problems, and the assessment. The MERM does, in the main body of heat exchanger design, has the equations for parallel and counterflow, but none others. I have, of course, the textbook had several tables of formulas, and I've used one of them in one of the places here. But I've tried to use problems that use the charts that are in the MERM. Okay, again, those are different charts than the ones we had for the LMTD correction, but similar kinds of things that you got to do. Okay. Okay, the term NTU, its equation is AU over C minimum. U is the overall heat transfer coefficient. A is the transfer area, so that's sort of the heat transfer part. The C sub minimum is really the smaller of either what is referred to as the CH or the C sub C, H standing for hot, C for cold. I could have added those to the subscripts, but the equation would have gotten a little long for the PowerPoint, but they are helpful if you're actually writing this out and trying to do this, solve this problem. So those are it. And what are they? Well, they are really m dot times the specific heat, mass flow rate times specific heat. So CH is m dot H times CPH. C sub C is m dot C times CP sub C. So you got those two, and that's going to be two of the things that you need to calculate first in many of the problems. Okay, and again, the way to think of the NTU, which is also going to be denoted as just N, at least in the equations. It gets a little bit cumbersome to keep using NTU, so people at least knowing that they're using this N, is the heat capacity of the heat exchanger divided by the heat capacity of the flow, because you've got the mass flow rate times the specific heat here. Okay, and then there's another quantity for the charts and also for the equations, C. So C and N are going to be our two things, and C is the ratio of the minimum over the maximum, and that can be, depending on the problem, it can be either the C sub C over C sub H or the C sub H over C sub C. It could be either way. So, but you want the minimum divided by the maximum. Okay. Okay, the actual heat transfer rate must reflect, again, that the energy given up by one fluid must be equal to the energy gained by the other. So in sort of the best argument I can give you without a lot that you might find in a textbook, but just this is part of it, is that you would have to use the C sub minimum, not the C sub max, in this particular equation as the Hn minus T sub Hn minus T sub Cn is, if you use the C sub max, you would end up with something greater, more possible than you would have. So you need to use the minimum. Okay, just take my word for that part. Is more to it than that. It may be in the argument, but it is in fact the case. Okay. Okay, and now using the definition then of the effectiveness epsilon, rearranging the equation, we actually can now come up with the actual heat transfer rate will now be epsilon times C minimum times the difference in those temperatures. Okay, so once we have epsilon, we're on our way. Okay. Okay, now remember again the heat transfer lost by one's got to be gained by the other. So just our regular m dot c sub p delta t kind of thing is the hot has to equal the cold heat transfer. So that again is there. So if you compare that one and the previous expression, you can come up with the following relationships between the effectiveness E and the temperature that you don't know. The first one, if you can kind of look through there, you know, there's N, but then there's TH out, the second term in the numerator. That's one you don't know. So once you know E, you know everything else. You can solve and come out with T sub H out. Actually, we'll actually do that here in a second, but this is how you rearrange the two formulas. The second term down there for epsilon, if you look through, notice there's a C sub H in the numerator, there's C sub min in the denominator of both of them, but notice again the first term in the temperature in the numerator, C sub C out, is the one we don't know. So you can, everything else we know, so we could solve for that and come up with it. And this, we can do that algebra, and I recommend that you do that. But one of the things now to have is that when you have two of the three parameters, you can find the other from either the equation or the charts. Usually you would you're going to know C and you're going to know N. You'll have calculated those, and so then you're going to look for epsilon. But there, I could conceive of, I didn't give you one, but I could conceive of one in which they gave you epsilon and they gave you C and they wanted you to find N, or they gave you epsilon and N and wanted you to find C from the chart. But normally what you're after really is the epsilon. Okay, that's probably the 95% problem. The other possibilities are slim, but they're possible. Okay, it could be. Okay, now for boilers or condensers, temperatures on the boiling and condensing side, remember, remain constant. That's just from your thermo, right? Kind of going from the saturated liquid to the saturated vapor. That's either the boiling it or condensing in that region. Okay, the temperature and pressure are not independent. Okay, so that's kind of from thermo, and therefore because of that, the C sub max gets very large. Well, if you in your definition, C is C minimum with C max. If C max starts getting really big, then C goes to 0. Okay, on that boiling or condensing side. Okay, so that's kind of a nice thing. And what happens is that if C goes to 0, then all the expressions for the effectiveness epsilon become a singular equation. Okay, it becomes 1 minus e to the minus n, where again n is really NTU, which is the AU over C minimum. It's very interesting. Again, the MERM only has parallel and counterflow equations, but in the reference I was using, I think I had 2 tables of equations, and I went through every one of them and put in C as 0, and yep, they all collapsed to 1 minus e to the minus n. It was remarkable. Some of them were really bizarre, but boy, you put in C as a 0, and you know, it just collapses. So kind of interesting. I didn't give you any examples or whatever, but I might want to keep that handy. Okay, as they all collapse to that one equation for the boiling and condensing side. Okay. Okay, so once this effectiveness has been determined, figuring that you're going to calculate the C, that's the ratio of the two C sub the min to the max, and that's just the m dot times C sub C or C sub C sub P of either of the other two. Once you have that, then your Q is that value epsilon times C minimum, which you've already calculated, and notice that you've got the two differences in the temperature, hot end minus the cold end, and you're given those, so you're on your way. Okay, now if you take those equations, and take this equation and the other two expressions and rearrange them, you end up with these two expressions for the two temperatures that you don't know, the TH out or the TC out. Okay, the TH out is the THN minus Q over C sub H, and the TC out is the T sub C in plus the Q over C sub C. And I recommend, I did this, I said to myself, well, okay, I got to do it. You know, some people do drugs, I do math. Not everybody, but I just said I got to do it. So it took about a half a page or so around, but it was nice coming down and getting those. You end up making friends with equations like that when you do it. So I recommend that you do that. Okay. Okay, well, let's look at an example here and do all the different things. What we want to do is determine the total heat transfer rate. That's, of course, capital Q for a counterflow heat exchanger where water is to cool oil. Okay, so the oil enters at 105 and 3 kilograms per second. Water enters at 15 degrees C and 0.6 kilograms per second. You see that you're not given any exit temperatures here. You're given the heat transfer area, 14.7 square meters. Again, some of these numbers so that things come out nicely are there. So it's just numbers I'm just picking. For the oil, use 2100 joules. That's a Newton meter per kilogram per degree C, and that's just a number from some specific heat table for kind of light oil or something. But again, it's just a number to use, but that's not too far off. And then for water at around this temperature, use C sub P of 4200. I think it's like 4180, whatever, but I thought let's just use 4200 and go on. Okay. The overall heat transfer coefficient is given as 600 watts per meter squared per degree C, and again, just a number you picked in order that things come out nicely. Okay. Okay. Well, we're off. Okay. And all these are going to follow the same sort of steps here. So this is one of the things that I want you to see is that this is how you're gonna march this way. There's not any variations here. You know, can I do it so and so? No, just follow these. Just do it. Okay. So let's find the CH and C sub C. So we're given the mass flow rate of the hot oil, and then we're given the m dot of the water, cold water 0.6. We're given both the CPs, 2100 and 4200. Multiply those out and get CH is 6300 watts per degree C and C sub C 2520 watts per degree C. So obviously the CH is bigger than the C sub C. So now C sub C is going to be our minimum, and our C sub H is going to be our maximum. So if we put that into our expression for C, 2520 divided by 6300 comes up exactly 0.4. Again, sort of played a little bit with the numbers so it would come out that way so you can read the chart a little bit easier. Okay, doesn't always happen, but for this one that it did. Okay, so now we got 1. So now we got C. Well, we need N. Okay, well, we can calculate N. We've got AU over C minimum. So we got the 14.7 meters squared, the 600 watts per meter squared degree C divided by the C minimum, 2520 watts per degree C. And again, this is supposed to be non-dimensional. So in the numerator, the meter squared cancels, the watts and watts cancel, and the degree C and the cancel as well. So you do end up with something, and this comes out to, again, to be nice 3.5. Kind of played with that 14.7 until it kind of worked out between those two. Okay, again, so it just makes reading the chart a little bit easier. Okay, so if you use those two and the chart in the appropriate chart in the appendix of the MERM, one of those 7 there, it fits. You get epsilon right at 0.92. I think fairly safe to read that chart. Okay. Now, it turns out this is, again, for counterflow, and this is in the body of the MERM and also in the reference that I was using, and I've kind of, again, used we've got N instead of NTU, and this particular expression put in the various values, 3.5 for N, 0.4 for C, and here this is where you've really got to be careful with your calculations. Have a TI 36 something another with multiple storage locations, so use that extensively to make sure of this calculation. I gave you some interim numbers there in case you have trouble with your calculator. 0.878 is the numerator, 0.951 is the denominator, and that came out right at 0.92. So the chart and the equation agree. That nice warm fuzzies with fuzzies there. Okay. Okay, so now we've got that. We now can calculate the Q. We've now got epsilon 0.92, the C minimum we've calculated already, 2520, and then the difference in the temperatures, 105 hot N minus the cold N, 15. Do that, get 208.66 kilowatts, which is approximately 209 kilowatts would be, if you had an ABCD, that would be, you might just have that 210. They might even have 200 as the answer. Okay, that's close enough. 200, 300, 400, 500, kind of a set of answers. Okay, so that 0.92, whether you read it 91, 92, 93, somewhere, if you that's all you had and you didn't have an equation, that would probably be just fine. Okay. Now, we weren't requested, although I do have you do this in one of the challenge problems here is count what are these outlet temperatures, both the hot out and the C out. Okay, so take these two equations that again derived and feel comfortable with. We now got the Q. That's why I've really got the 28.66 kind of thing to get to accuracy here, keep the accuracy going. So for the first one, we've got 105 minus the 208.66 kilowatts divided by, now we got to take our C sub H's that was like 6,300, and now it is 6.3 kilowatts per degree. So we get them both in kilowatts and we end up with degrees C, and what we end up with is 105 minus 33, which gives 72. So it drops 33 degrees, so down to 72. Okay, so we got that. And then similarly for the water, in this case though, you've got T sub Cn plus Q over C sub C. Notice it's THN minus Q over C sub H. So the H is up there, the C's down here. And when you do the second term, you end up with plus 83 degrees. So this almost gets it to boiling. Okay, 15 plus 83 degrees gives you 98 degrees C. Okay. Okay, now one of the things just occurred to me is that we could also calculate the Q now that we do know these temperatures, is sort of verify that everything kind of works out. The old m dot delta H kind of thing is or CP m dot CP delta T is let's look at both of these and see if we come out. So on the hot side there, the CH, which is m dot CP times delta T, we've got 6,300 times the 105 minus 72, and we get 207.9 is about 208. So we're 1 kilowatt short, but again, there's some round off in all of this as well. If we do the water, we get a little bit more than 209. The 2520 times again the 98 minus 15 gives us that. So we're all right there. Okay, this is just round off. I just did whole numbers on the temperature. So so that's all. That's why we have, I think, a little bit of variation here. So all that got warm fuzzies. Okay, that we got the same Q from this, the temperatures and all of that. Okay, so and this is the way it goes. Okay, this particular problem, this is how it flows. Blop blop blop, step by step. So make sure you've got this in your PRN under heat exchangers there. Okay. Well, that concludes this lesson for week 18 of the thermal fluid systems. As always, we appreciate you allowing us to help you prepare for this exam.